Okay, guys, so the servers for the Pencast are still not working, so I thought I would do something a little bit different to prepare you guys for tomorrow's lab, where you'll be measuring the rate of a chemical reaction, in particular, a reaction um, that is called the iodination of acetone. So recall from lecture that for a reaction, A plus B going to C, the rate law can be expressed as the rate equals K, the rate constant, times the molar concentration of A raised to the M power, times the molar concentration of B raised to the N power. Recall that M is the order of the reaction with respect to A, and N is the order of reaction with respect to B, and overall, M plus N represents the order of the reaction itself. Now remember that M plus N, or M and N, must be determined by experiment. Okay, they do not correspond to the coefficients from the balanced chemical reaction. Now there is a strong temperature dependence with rates of chemical reactions. There's something called the Arrhenius equation, which takes the form as shown here. And notice that it's very similar to the Clausius-Clapeyron equation in that we have the natural log of some number, in this case k, the rate constant, equals negative E sub A divided by R times 1 over T plus some constant. So in this case, natural log of the rate constant k is like y, 1 over T is like x, and this ratio of E sub A and R is the slope of that line if we were to plot it out. Now E sub A is called the energy of activation, and it's the minimum energy required for the reaction to proceed. So if we were to plot out a series of data of natural log k versus 1 over T, the slope of that line would be negative activation energy over R, and we could very easily calculate the activation energy just by taking the quantity of the slope and multiplying it by negative R. However, we're not going to have time to actually measure the rate of the reaction at different temperatures and get the data needed to plot out the Arrhenius equation. So we're not going to do that in lab, but we'll be going over this in lecture. So shown here is the chemical equation for the reaction that you'll be doing in lab. On the left we see acetone reacting with iodine, and we get iodoacetone, where we can see that there's been an iodine substituted on. We also get hydrogen ion and iodide anion, I minus, as products. We could go ahead and write out the rate law for this reaction as shown down here, where the rate equals the rate constant times the molar concentration of acetone raised to the M power times the molar concentration of iodine raised to the N power times the molar concentration of hydrogen ion raised to the P power. Now note that hydrogen ion does not explicitly appear as a reactant in the chemical reaction up here, but it is nonetheless part of the rate law because the reaction is pH dependent. We've just chosen not to write its dependence here in the reactants. Also recall from lecture that we could express the rate mathematically as the negative change in the concentration of one of the reactants, in this case iodine, divided by the change in time. Now iodine makes a really good metric in this case because it's colored as I2, and then in the products as I minus, it's not colored. So we can visibly determine when the reaction is done just by looking for a loss of color. Now as it turns out, the rate law for this reaction is zero order with respect to iodine. So N equals 0, and iodine essentially drops out from the rate law. Now because of this, and because we're going to be using iodine as the limiting reactant in this equation, we can go ahead and re-express the rate as shown here, where it's the initial concentration of iodine divided by time. Okay? Now it's just the initial concentration of iodine because it is the limiting reactant and it will be completely consumed by the reaction. And so the change in the iodine concentration is essentially equal to its initial concentration. Writing out the rate law once again under conditions 1, so rate 1 equals the rate constant times the molar concentration of acetone under the first set of conditions raised to the M power times the molar concentration of iodine raised to the 0 power because it is 0 order times the molar concentration of hydrogen ion raised to the P power. And then we can repeat the experiment under a second set of conditions and get a second rate, where rate 2 is equal to the same rate constant, K, times the molar concentration of acetone under these new second conditions raised to the m power, again times the molar concentration of iodine to the 0 power, times the molar concentration of hydrogen ion to the p power. So if we go ahead and make a simplifying judgment in this case, where in the first set of reaction conditions for rate 1, we go ahead and just double the concentration of acetone for rate 2. So in that case, the concentration of acetone under the second conditions is equal to 2 times that of the concentration of acetone under the first conditions. And remember from lecture, we can take the ratio of those two rates and very, very nicely cancel out a bunch of the variables here so that we can get a bead on what these exponents are in the rate law. So if we write the ratio of rate 2 to rate 1, we get an expression as such, shown here. And pretty much everything drops out. So the rate constants are equal, so they drop out. The iodine concentration drops out, and the hydrogen ion concentration drops out, as long as we're careful to keep those concentrations exactly the same between these two different experimental conditions. So this ratio of rates simplifies down to the concentration of acetone under conditions 2 raised to the m power divided by the concentration of acetone under conditions 1 raised to the m power. We're going to go ahead and substitute 2 times the concentration of acetone 1 for acetone 2, and that transforms the equation into how we see it here, where we have the quantity of 2 times the concentration of acetone under the first conditions raised to the m power divided by the concentration of acetone under the first conditions raised to the m power. And of course, this further simplifies to just 2 to the m. And the whole messy equation nicely simplifies down to the rate that we calculate under conditions 2 divided by the rate that we calculate under conditions 1 equals 2 to the m power. And as we saw in lecture, we can very simply solve for the exponent m here and get the order of the reaction with respect to acetone in this case. So again, taking the equation that we saw on the last slide, rate under conditions 1 would equal the initial concentration of iodine divided by the time that we measure for the color of iodine to disappear, so T1. And under the second set of conditions, rate 2 would equal the initial concentration of iodine divided by the time that it took for the color of iodine to disappear. So we can very easily calculate the two rates. Now note that these concentrations are not the 0.005 molar or whatever concentration is labeled on the bottle of iodine in the lab. Okay, these are the concentrations of iodine once you mix up your reaction solution. And so we need to invoke that dilution equation that we learned in lecture to go ahead and calculate the concentration of iodine in the reaction solution based on knowing the original concentration and the total volume of the reaction solution. So let's see how we do that. So recall that the initial molarity times the initial volume is equal to the final molarity times the final volume. And if we rearrange this, we get the final molarity, which is the concentration of I2 in this case, equals the initial molarity times the initial volume divided by the final volume. So for iodine, we have the initial concentration of iodine is going to be equal to the concentration from the bottle, in this case 0.005 molar, times the amount that we added to the reaction solution, in this case 10 milliliters, divided by the total reaction volume, in this case 50 milliliters. And so the initial concentration of iodine turns out to be 0.001 molar. Okay, so be aware of that. We need to go ahead and recalculate the concentration of iodine based on the total volume of the reaction solution. Okay, so we collect some data as described in the lab manual procedure, which the procedure itself is actually fairly clear. Okay, so let's say we have our initial concentration of iodine, as we calculated on the previous slide, to be 0.001 molar, and we measure a time of 187 seconds for the color of iodine to disappear. So as we saw on the previous slide, we can express the rate under these first conditions as the concentration of iodine divided by the time that it took to lose the color of iodine, And in this case, we get 5.3 times 10 to the minus 6th mole per liter second. Okay. Now I know my significant figures are off here, but the book is using all kinds of numbers with 1 sig fig, and I want you guys to go ahead and report at least 2 sig figs for all of your calculations. So you'll do this under your first set of conditions, and then you're going to repeat this rate determination. Again, it's rate 1 using the same conditions. Okay, and this is what your lab manual is referring to as mixture 1. So for each mixture, you're going to calculate the rate 2 times, just as a check for error. Okay? And then the rate under those conditions will just be the average of the two. And I believe your lab manual suggests that those two numbers should be within 15 or 20 seconds of one another. Okay, so you go ahead and calculate the rate based on the 2 observations for mixture 1. And then you're going to go ahead and determine the rate where we're going to vary the concentration of acetone. Okay, so as we saw when we were deriving the equation, what we want to do is we want to double the concentration of acetone and keep all of the other concentrations the same. So double the concentration of acetone, the concentration of iodine, and the concentration of hydrogen ion, H+, will remain the same as that in mixture 1. Okay, so you'll mix those together. You'll determine the rate. Again, determine the rate 2 times. And that will be mixture 2. And then you're going to determine the rate by varying the hydrogen ion concentration. Okay, and in this case, we're going to keep the acetone concentration and the iodine concentration the same as they were in mixture 1. Okay, and we're going to go ahead and double the concentration of hydrogen ion versus what it was in mixture 1. And this is what your lab manual is referring to as mixture 3. And again, you're going to determine that rate twice, just as a check for error. And then lastly, you'll determine the rate where we're going to double the concentration of iodine over what it was in mixture 1. Okay. Again, you're going to do this twice, and this is what your lab manual is referring to as mixture 4. So again, for mixtures 2, 3, and 4, make sure to keep all the other concentrations the same as they were in mixture 1. Okay, so when you double the concentration of acetone for mixture 2, you want to make sure that the concentration of iodine and the concentration of hydrogen ion was the same as the case in mixture 1. And then for mixture 3, you want to make sure that the concentration of acetone and the concentration of iodine were the same as in mixture 1. And for mixture 4, you want to make sure that the concentration of acetone and hydrogen ion were the same as they were in mixture 1. Oh, I see a typo right here. Sorry. Okay, so you're going to determine the rates under each set of conditions twice for mixture 1, mixture 2, mixture 3, and mixture 4. Okay. And as we saw, the ratio of the rates, the second set of conditions to the first set of conditions, is equal to 2 to the m power. Okay, and m specifically is referring to acetone in this case, but we can replace this for for iodine, and we can replace m with p, and it will be representative of the hydrogen ion concentration. Now remember from lecture, we have an unusual base here, and we need to solve an unknown exponent of that unusual base. So we can rearrange this, and using the laws of logarithms, we can say that m is therefore equal to the log of the quantity of the ratio rate 2 to rate 1 divided by the log of 2. Okay, so remember, if you want to change the base, it's just the log of this number divided by the log of the unusual base. Okay, so for acetone, rate 1 in this equation is determined from mixture 1, and rate 2 is determined from mixture 2, where you doubled the concentration of acetone and kept all the other concentrations the same. For H+, rate 1 is also the rate from mixture 1, and rate 2 is the rate from mixture 3, where you doubled the concentration of hydrogen ion and you kept everything else the same. And likewise for iodine, rate 1 is from mixture 1, and rate 2 is from mixture 4, where you doubled the concentration of iodine and you kept the concentration of everything else the same. Okay, that's it. I hope this helps out. The lab should go relatively smoothly. There's a little bit of math and quite a bit of calculations that you have to do, but they're all pretty straightforward. Okay, so once you get all of your rate data, you can go ahead and calculate the order of reaction with respect to acetone, which is M, with respect to iodine, which is N, and with respect to hydrogen ion, which is P. Now we already know that the reaction is 0 order with respect to iodine, and we're just doing this last measurement to verify that N is 0 or that the reaction is 0 order in iodine. Okay, I'll be just down the hall tomorrow when you guys are doing the lab, and I hope this really helps you guys out in preparation for the lab. Hope you had a good weekend. See you tomorrow.